Today we continue the earlier article Zeeman effect. In this article, we explain about the anomalous Zeeman effect. That term include the resultant magnetic moment, Landé factor, magnetic interaction energy, and complete term value of a magnetic level. All these terms we discuss here one by one according to vector atom model and Landé's Z factor. Now, what is that theory? If we introduce the spin motion of an electron, that term we discussed earlier, and it shows the splitting of the energy level gets resulted due to introducing spin motion of an electron. But here the spin motion of electron, that concept is introduced along with external magnetic field. Then what happened? According to Zeeman, it proves that this single spectral line is split into multiple component lines in presence of weak magnetic field. That effect is known as anomalous Zeeman effect. This effect we theoretically prove how the single spectral line split into multiple component lines. Hence, we consider the spin motion of an electron and we use the vector atom model. According to that theory, initially we show that the L star and S star, these two vectors which precise around their resultant vector J star. If the field is weak, the coupling between L star and S star is not broken and hence they precise about the resultant vector J star. The resultant vector J star is the sum of L star plus S star. Due to orbital motion of an electron, and if that electron is precise around the resulting vector J star, it produces the magnetic moment. That magnetic moment is due to orbital motion. It is equal to PL multiplied by h divided by 2 pi. PL is again integral multiple of h divided by 2 pi, and we simplify that term. Mu L is equal to L star EH divided by 4 pi m, where L star is equal to under root L into L plus 1. Similarly, the magnetic moment due to spin motion of an electron is twice S star EH divided by 4 pi m, where S star is under root S into S plus 1. Here in that diagram, we show that L star and S star is precise about the resulting vector J star. Due to orbital motion, it produces magnetic moment, but that magnetic moment is opposite to that of L star. Similarly, mu s is also opposite to that of S star, that are due to the negative charge on that electron. Here, the mu L and mu s are oppositely directed to that of PL and PS respectively, as well as they precise around the resulting vector mu j, but that resulting vector is not in the line of the resultant of total magnetic moment of due to mu L and mu s. Now, why it is not in the direction of the resultant of mu L s? Since here the inequality is shown here, that means the ratio mu s by ps is always double to that of mu L by PL. And due to that inequality of the two ratios, the total magnetic moment mu ls is not exactly antiparallel to resulting vector j star. If it is not exactly antiparallel, then it is necessary to find the resulting value of this mu j. That term we have to find firstly. To find the resulting value of the magnetic moment due to total quantum number j, that is mu j, we resolve mu ls into the two directions. Which this two direction we just take? The one is mu ls is perpendicular to j star. And if mu ls is perpendicular to j star, then what happen? They precise continuously by changing the direction. And if it continuously changes direction, its average is taken to be 0. While in the other condition, if the resulting vector mu ls is parallel to j star, then that component it should be added due to orbital magnetic moment and spin magnetic moment. Hence, we find the resulting value of mu j must be equal to the component of mu L along J star plus component of mu S along J star. Now, how we write the component of mu L along J star? That means we take the projection of mu L along J star. It gives the term mu L into cos of L star J star plus second term component of mu S along J star. Here also mu S is projected on J star and it gives mu S into cos of S star J star. Mu L and mu S, that two terms we defined earlier, that value we directly put here and we rewrite the equation. E into H divided by 4 pi m L star cos L star J star plus twice EH divided by 4 pi m S star cos S star J star. Now we simplify. Now what is the value of cos L star J star and cos S star J star? These two terms we write by using the cosine rule or the cosine law here. Cos L star J star is equal to J star square plus L star square minus S star square divided by twice L star J star. And cos S star J star equal to J star square plus S star square minus L star square divided by twice S star J star. Now put these two terms in this above equation. We get mu j is equal to EH divided by 4 pi m. We take common for both the term and simplify L star cos L star J star and S star cos S star J star. The bracketed term becomes J star square plus L star square minus S star square divided by twice J star. L star numerator denominator get cancelled here plus twice J star square plus S star square minus L star square divided by twice J star S star. S star numerator denominator cancel and we get that term. Again simplifying bracketed term by taking LCM twice J star. Numerator terms firstly simplify and we get EH divided by 4 pi m into bracket 3j square plus S star square minus L star square divided by twice J star square. Again we simplify the bracketed term by simplifying 3j star square taken as 2j square plus j square. It becomes 3j square. Other two terms we keep as it is. S star square minus L star square divided by twice J star Now we separate first term in the bracket twice j star square divided by twice j star. 2 cancel. J star is only remaining in the numerator. That term we take outside means it is take common. The first term becomes 1 plus j star square plus s star square minus l star square. If j is common, here denominator term we multiplied by j and it becomes divided by twice j star square. In that equation, the constant term eh divided by 4 pi m is denoted by beta, that constant known as Bohr magneton. And the bracketed term 1 plus j star square minus l star square divided by twice j star square, that term gives another constant term, that is Landé's z factor. Hence, for calculating the resulting value of mu j, we get one more equation, and that equation is relation for Landé's z factor. That relation is 1 plus j star square plus s star square minus l star square divided by twice j star square. Now, what is its physical meaning of that term? It gives the relative separation of Zeeman levels of different terms. Means if the single state gets splitted into multiple levels, in that case it plays very important role to the splitting of each Zeeman level. G is equal to 1 plus j star square plus s star square minus s star square divided by twice j star square. Hence, Landé's z factor, this is an important term to explain the anomalous Zeeman effect, since in that case electron spin is introduced. Suppose we say in that case, if the spin, electron spin we neglecting here, then what happen? If we suppose S is to be 0, S is to be 0, then what is the J star J here? J term is L plus S. S is 0. S is 0. J equal to L plus S means it is again J equal to L. Hence, in that equation, S is 0, J is equal to L. Hence, first and last term gets cancelled. Numerator term is 0. Total term is to be 0, and we get simply G is equal to 1. It means that equation, if G is 1, the equation again reduces to normal Zeeman effect. Since in the normal Zeeman effect we discussed earlier, electron spin is not introduced for explanation of that effect. But for anomalous Zeeman effect, if we introduce the spin motion of an electron, we get the additional factor. That factor is Landé's z factor. This is due to magnetic interaction. And due to that magnetic interaction, the each Zeeman level gets splitted into multiple component lines. That interpretation is for Landé's z factor. Nextly, we find the magnetic interaction energy. Now, what is the magnetic interaction energy? If the field is very weak and L star and S star are precise about their resulting vector J star, then the coupling between L star and S star is not broken. They continuously precise about the resulting vector J star. It means J star also precise about the resulting magnetic field B. That B is the external magnetic field. Then what is the interaction energy between, if the J star total quantum number which precise about the resulting field B, then the interaction energy it gives the projection of the total magnetic moment on external field direction. That projection we write mu j b cos of j star b. Since b multiplied by the strength of magnetic field multiplied by the projection of total magnetic moment on external field direction. That relation is mu j b cos j star b. Interaction energy we denote delta W, and we simplify the relation. Again mu j, that value we find earlier, this is j g Eh divided by 4 pi m. B is as it is, cos term is as it is. Eh divided by 4 pi m is Bohr magneton, or we keep as it is here. Hence j, again we simplify that relation. Once we put the value of mu j, j g Eh divided by 4 pi m b into cos of j star b. In that j cos of j star b is the projection of j star on external field direction. And you know we get this component, z component in that case, and that is mj. Hence mj represent magnetic total quantum number. In terms of magnetic total quantum number, the interaction energy is mj b g Eh divided by 4 pi m. Now what is that mj? Mj takes how many values? 2j plus 1, since it depends upon the value of j, and these values are extending from minus j to plus j. This is about the magnetic interaction energy. Magnetic interaction energy we get delta W is equal to mj b g into Eh divided by 4 pi m. That relation we use for calculation of the next term, that is the term shift in wave number. According to the standard relation, term shift in wave number minus delta t equal to interaction energy, change in magnetic interaction energy, that is delta W. That term we calculate earlier, divided by Hc, and we simplify the term mj b g E divided by 4 pi m c. In that case, E into B divided by 4 pi m into c. This is again one constant. That constant we express in terms of Lorentz unit, and that Lorentz unit is EB divided by 4 pi m into c. Hence what is L here? L is E into B divided by 4 pi m into c. Hence in terms of Lorentz unit, the Zeeman splitting is minus delta T is equal to mjgl. That splitting is due to magnetic interaction energy in terms of Landé's factor G and Lorentz unit L. Hence, what is the complete term value of a magnetic level? That we define here, T equal to T0 minus tau minus delta T. But tau is fine structure shift that we discussed earlier in the normal Zeeman effect. MJGL is the term shift due to magnetic interaction. And both the term shift due to fine structure and due to magnetic interaction, we have to define the complete term value of a magnetic level. Now, if we know the complete term value and we show how the single level is splitted into multiple sub-levels, then it is necessary to know what is the selection rule. That selection rule depends on the magnetic total quantum number mj. Hence, delta Mj should be 0 or plus 1 or minus 1. Now, when we get delta Mj 0, when it is plus 1 and minus 1, it depends upon our observation view whether it is perpendicular to B or parallel to B. Hence, firstly say if view is perpendicular to magnetic field and delta ML equal to 0, then the resulting spectral line gets plane polarized and its vibrations are parallel to B. That component is pi component. And if delta ML is plus 1 or minus 1, then again resulting vibrations are plane polarized and that component is sigma component. Secondly, if the view is parallel to magnetic field, delta ML is 0, it means that transition is absent. Such a transition absent known as forbidden transition and denoted by pi component. In parallel view, again delta ML is plus minus 1. The resulting vibrations are circularly polarized. That component is sigma. Hence, using that selection rule, how the splitting of the spectral lines takes place in actual given element, that we explain by considering one of the example of the sodium D line. We know how the D line, sodium D line we get when the transition takes place from L equal to 1 to L equal to 0. Now that is the one of the spectral line. That spectral line is sodium D line. Now that single line gets splitted into doublet. This is the doublet that we explained earlier. This is due to fine structure shift. Single line splitted into two lines, D1 and D2. D1 is the transition due from doublet P half to doublet S half. This is D1. And doublet P 3 by 2 to doublet S half, that is D2. But that D1 line again splitted due to magnetic interaction. That means this is due to term shift in due to magnetic interaction MJGL. That is shown here. If we suppose L0 means it is WTS half state in presence of magnetic interaction, magnetic field in anomalous Zeeman effect, it gets splitted into two lines. Now how we get it is two lines? Since the magnetic interaction Mj, it gives 2j plus 1 values. And for L equal to 1, L equal to 0, this is only one state, WTS half. For that one, j is half, hence 2j plus 1. 2 multiplied by half, that is 1. 1 plus 1, we get 2. Hence, WTS half in presence of weak magnetic field gets splitted into two lines. Lower one is Mj is minus half, upper is plus half. Similarly, we split doublet P half term. Again, it is splitted into two lines. And doublet P 3 by 2 splitted into 2j plus 1 means j is 3 by 2. 3 by 2 into 2, that is 3. 3 plus 1, 4. We get splitted into 4 lines. Which are these 4 lines? Lowest one is minus 3 by 2, mj equal to minus 3 by 2, minus half, plus half, 3 by 2. It means due to magnetic interaction, L equal to 1 splitted into multiple component lines. And within these sublevels, which transitions which are spectroscopically allowed or not, that we decide by using the selection rule. Using that selection rule, D1 is splitted into 4 lines and D2 is splitted into 6 lines. Such a multiple component lines we are observing under the weak magnetic field, and that is the result of the anomalous Zeeman effect. Thank you.